Babit, we're going live on YouTube. Are we live?
Okay.
Yeah, I think we're live. Okay, so welcome to our fifth webinar, and that is by Dr. Akash Saraogi from RELIANCE Foundation, Mumbai. And it's a FRCS oriented live webinar. And I welcome Akash to this webinar. And he's going to talk about tribology and applied basic science and with respect to total hip replacement and knee replacements. So welcome, Akash. So let's go ahead.
Thank you for that introduction, sir. Should I share my screen? Is that okay?
Yeah.
Okay, are we able to see this?
Yeah, we are. You're online. Go ahead.
Right. So good afternoon, everyone. I welcome you all to this talk on basic sciences. And we are going to touch upon a bit upon the tribology, which is material properties in arthroplasty. We'll also touch upon few things which relates to stress and strain of the materials. The reason why we talk on this topic is two things. Number one, that this can be a make and break topic in your FRCS exam, which means that if you perform very well on this topic, you can score an 8, which is the highest. And if you do not perform well in this topic, this can end up in a failure. The second reason why this topic is important is because it is a basic science topic. It does not change. So more or less the questions, the answers, the format remains the same, which means we can prepare for this well in advance with no surprises, right? So let's begin with this. Right. So the first thing that can be asked is to describe the stress and strain in the form of a curve. So what exactly is a stress? It is a force applied to a particular object in a unit area. So is stress same as force? No, it is a force, but applied to a per unit area of an object. Now, an object can be isotropic or anisotropic. What isotropic means is that if I take an object and if I apply a pressure from this direction or this direction or this direction, it does not make any difference to the object. It will react the same way irrespective of the direction of application of the force. And that object is called as an isotropic object. Whereas an anisotropic object like this on the scale, if I apply the pressure from here, it will behave differently. If I apply the pressure from here, it will behave differently. So this is an anisotropic object which behaves differently depending upon the direction of application. Most of the structures in our body, like the cortical bone, the cartilage, all these objects are anisotropic objects. Okay. Now, what is strain? Now, strain is change in length with respect to the original length. So if this was the length of the rubber band, and if I pull it like this, there is a change in length. Now, this change in length, when I divide it with the original length of the object, that is called as strain. Because it is a ratio, there is no unit for the strain. When we plot this stress against the strain in the form of a curve, that becomes our stress strain curve. And the finding, the number that we get, which is the coefficient, is called as the Young's modulus. So this is a typical stress strain curve. And if you understand this in basic science, you understand everything about tribology. So here you can see on the x-axis, we have plotted the strain, which is the change in length. On the y-axis, we have plotted the stress, which is the increase in the force per unit area of the object. So let's take this typical material where we are applying this pull. So we are changing the length of this object. So there is an increase in the strain of this object. When we are increasing the strain, because this is under tension, there is also increase in stress of the object. Suppose I leave this stress, this comes back to its original length. So this is this elastic region of this particular object, where increase in stress coincides with the increase in the strain of the object. right? And it is proportional to each other. The more the increase in stress, the more is the increase in the strain. But can we stretch it indefinitely? The answer is no. At some point in time, it is going to break. Similarly, if we take a piece of plastic, so this is a piece of plastic. If I stretch this and I stretch it further, it breaks. But there is a point where it is stretching and just staying the way it is without recoiling back to its original shape. Now, this is called as the plastic region. Now, what this dark blue that you see over here is the elastic region, and anything beyond is the plastic region where the object cannot come back to its original state. The point in between the elastic region and the plastic region is called as the yield point. This area is called as the yield point. Now, there are three things which happen at the yield point. Number one is the proportionality limit. What does it mean? That up till now, the increase in strain was proportional to the increase in stress. More the stress, more the strain. But when we reach this point, even if there is very little increase in the stress, the strain may increase significantly, which means that they are not proportional to each other. One may increase more than the other. Okay, so that is a proportional limit. The second point that we see over here is the elastic limit. What does elastic limit mean? From this point onwards, if I apply more stress, this object is going to change from an elastic to a plastic. So any stress above the elastic limit is going to cause a permanent deformation of an object. The third thing that we see is the yield stress. What does yield stress mean? Yield stress means the minimum amount of stress that I should be able to apply to see a deformation. At elastic limit, we know that the substance will become from an elastic to a plastic. But at a yield stress level, that much stress, I can see the deformation of the object. So that is a yield stress. For all practical purposes, all of these 3 points coincide at one particular point. That point is called as the yield point. Now, after the yield point, the substance is going to increase in length, without significant rise in the stress level. So if you see this area where it is yielding, means giving away in length without causing much of stress increase. But after a particular length, the stress again starts to rise in this object. And that particular phase is called as strain hardening. And this is what is used to make all our materials, whether it is a metal, whether it is a plate, whether it is a joint, whether it is a stem. We use strain hardening of the metal to give it the ultimate strength, because strain hardening makes the material very, very stiff and does not let it deform. There is only a particular point up till which you can do a strain hardening. If you do strain hardening too much, that's what happens, which is a failure. So logically, you might ask me that this failure should happen at ultimate stress. Why should there be any decrease in the stress further before it fractures? Why is this fracture not at the ultimate stress? Practically speaking, this fracture is at the level of ultimate stress. But you need to know that this fracture is happening at one particular point, whereas the graph is measured for the entire material, which means that when the plastic is going to fracture at this particular point, the other area, the stress is going to decrease. Why? Because at this point, all the stress is now concentrated to fracture this plastic. All the remaining areas, the stress decreases, and that's why we get this downward slope in this curve. And this phenomenon is called as necking, right? So we'll proceed from here. So this is again a stress strain curve, and this may be put in your exam and asked you, okay, can you tell me about what material this is, what stress strain curve this is? So if you see, typically there is a toe region over here, This toe region implies that there is an increase in length of this material in the beginning without increase in any amount of stress. So this is a graph of a ligament or a tendon. Now there are collagen fibers in both ligament and tendon, and these collagen fibers are not under tensile strength. These are wavy. So these are wavy collagen fibers, which is called as crimp, C-R-I-M-P, crimp. Now, whenever we apply a stretch to a tendon or a ligament, there will be uncrimping of the fibers, which means this wavy fibers are going to become straight. And this will give some strain, which is increase in length, without causing any increase in the stress of the tendon, which is called as the toe region. So no increase in stress, only increase in the strain. And then it proceeds like a normal stress strain curve. So we'll talk a little bit about the material properties, that some materials can be strong, hard, tough, brittle, ductile. Are these all the same? The answer is obviously no. So let's look into what each of these buzzwords mean. So what does ductile mean? Ductile means that you can bring about a large amount of plastic deformation before failure, right? So for example, if this was a ductile material, it will continue to stretch before it completely fails, right? Remember, the deformation is plastic, not elastic, which means that it is going to continuously increase and it is never going to come back to its original shape. What does brittle mean? Brittle means that that particular material has got no plastic deformation at all, right? So if I try to bend this, this is quite elastic. But if I bend it a lot, this is going to directly break. This is not going to form a permanent deformation. And this is known as brittle, especially ceramics. So ceramics they have no plastic potential where you can stretch them. They will directly fail. So that's brittle. What does stiff? Stiff means that the stress rays is much more as compared to the strain rays. So this particular graph, if the graph was plotted in this direction like this, which means the stress is increasing much more than the strain, that material is called as a stiff material. What does tough mean? Tough means if I impact something, the amount of energy it can absorb before it fails, that is tough. How do we measure this? We see the area under the curve. All the area which is there under the curve, that is the area which defines the toughness of the material. What is hardness? Now, hardness is not a material property. It is a surface property. How good is the surface of a material is what determines the hardness. How much is it resistant to scratching or deformation? That is what is hardness. Whereas strength is of the entire material, not just of the surface. Right. Another thing which will be asked in the exam very commonly is to draw a fatigue failure curve. Now, whenever we are using a plastic or a metal in a hip replacement, when will this plastic fail? How will you determine this? So this is the graph that we draw. And this graph is called as the SN curve, right? What does the SN curve tell us? It tells us the endurance limit of that particular material. If I bend the scale with a very significant stress, it is going to break away in the single cycle. If I bend it 200 times like this, maybe when we reach 200, it is going to fail. But any material, the amount of stress that it will take to apply 10 million times, if I do this 10 million times and then it fails, that is the endurance limit of that particular material. So any material when we make for arthroplasty, we need an endurance limit of minimum 10 million cycles. 10 million cycles is roughly equivalent to 10 years, which means that any material which we use for hip or knee replacement, we want that material characteristic to be minimum lasting for 10 years. That is what it means, the endurance limit. So how many cycles are needed? 10 million cycles. Now, what does viscoelastic means? Viscoelastic is two words, viscous and elastic. We know what is elastic. It is temporary and it can come back to its original shape. But what is viscous? Viscous is permanent. Now, what is the difference between viscous and plastic then? The difference is the time. If I'm moving something too fast, the stress and strain curve is going to be different as compared to when I'm moving it at a moderate speed, as compared to when I'm moving it at a slow speed. So viscous is a time dependent permanent deformation of a material. So to show you in this, so same material, we are applying a load too fast, moderate, and too slow. And the pace or the amount of deformation differs based upon the time of the rate of application. So the viscous materials or viscoelastic materials have got few special properties. And this is the most important applied basic science of this particular topic, right? Because in the exam, they will ask you, what is creep? Now, what is creep? Suppose it is a time dependent deformation. So if I have kept something for a particular time at a particular stress, the deformation is going to change. I'll explain you with a very simple example. Now, when we use an Exeter stem in cemented hip arthroplasty, we have put the stem inside, which means that we have put a particular load or stress into that bone for a particular amount of time. After few months or years, we see that the stem subsides. And this is a typical example of a creep. The load is constant. That does not change. The Exeter stem weight or the load is going to remain the same. But that load under a period of time is going to change the length, which means that it is going to subside. And this phenomenon is called as creep under constant load. What is the second example of this? Another example could be the ACL graft. Now we do repeated cycling motion of the ACL graft before we fix it onto the tibia, the interference screw, or the final insertion of the tibial fixation. So what happens in that, when we are cyclically loading, the load is going to be constant on the graft. But after repetitive loading or cycling loading of the graft, it is going to form creep or change its length over a period of time. And that's why we use creep phenomena when we are doing the ACL fixation. The second graph that you see is stress relaxation. What happens over here? The strain is constant. In the previous example, the stress was constant. In this example, the strain is constant. Now, suppose if I pull this rubber band, so if I pull this rubber band to a constant length and just hold it like this for the next 10 years, of course, there is some tension in this band. There is some stress within it. The stress which is there now is going to reduce over the period of 10 years. After 10 years, the rubber band is not going to be under so much of tension. It will be under less tension. And that is called as stress relaxation under a constant strain. Now, where do we use this concept in our clinical practice? Two places. Number one is when we are tapping the stem of the femur. Typically, you must have noticed your consultant telling you that tap, 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 just wait for 2 minutes, let it expand, let it relax, and then you tap again. Now, actually, it does not expand when you are tapping again. What happens is whatever expansion has to happen has happened already when you have done the initial tap. The stress is very high because there is a hoop stress happening on the stem of the femur. Now, that stress level goes down after a few minutes, because if you hit the ultimate stress in the very beginning, the stem is going to fracture. That's why you want that stress to come down. You want a stress relaxation like this so that you can tap again and you can increase the stress again and get the stem down. So this is one example. Second example would be Ponseti casting. What you do, you strain. There is a fixed amount of strain that you have applied. Because of this strain, there is going to be some stress within the ligaments. But after a week or so, the collagen fibers will form the crimp again, which means that the stress within is going to relax so as for you to apply the new strain again. Suppose you did the final correction in one go, what would happen? The ligaments and the tendons will reach their ultimate stress and they will buck. So this is the second phenomenon which is very important, which is stress relaxation. The third thing which we'll talk about is hysteresis. Now, what does hysteresis mean? That when we load an object and when we unload an object, the stress and strain curve may not be the same path. You expect them, the stress to rise and to come back through the same channel. It does not happen like that. If you see this graph, it is going up over here and then coming back by a different route. Why does this happen? Because in the process of loading and unloading, you lose some energy in the form of heat. And that is what is called as hysteresis. Let's move on. So this is an example of what I was talking about, the hoop stress. If you were to fill a gallon of water, a big one, because of the amount of stress, the wooden plank may just burst away. To prevent that, we are given this circumferential iron railing, which will distribute the hoop stress. Right? Now, you will be asked to draw Young's modulus for the cartilage, Young's modulus for ceramic, Young's modulus for stainless steel. So they can ask you to draw Young's modulus for any material. Now, it is very difficult to remember the stress strain curve for each of these materials. What is the easiest way to depict this? It is this. You have x-axis as strain, x-axis as strain, y-axis as stress, and you have depicted all the materials in one go. So this is the 1 stands for ceramic, as we can see over here. The 5 stands for the cortical bone. The 4 stands for titanium. So these are the Young's modulus based on differences in stiffness of all material, where ceramic is the one with the highest Young's modulus and cartilage is with the lowest Young's modulus. If you see, we always say that titanium is closest to the bone, steel is not, titanium is closest to the bone. What does it mean? The Young's modulus of titanium, which is 5, is closest to that of the cortical bone, which is 6. Okay, we'll talk a little bit about the cement. Now, what cement do we use? We use a polymethyl methacrylate cement. It comes in 2 phases, the solid form and the liquid form. The only important thing to remember over here is the solid form is radio opaque because of the presence of barium or zirconium dioxide. The initiator is in the solid form, whereas the inhibitor and activator is in the liquid form. So remember, the initiator is in the solid, whereas the activator is in the liquid form. Which is the liquid monomer? It is the DMT, NN dimethyl toluene. Right? What happens when they mix? There is an exothermic reaction. We all know about the different 4 phases. We also know about 3 different generations of cementing. So I'm not going to go much into that. Right? So coming to the next important topic, and I think this is the most important topic in tribology of arthroplasty, which is how is your plastic manufactured? Who was the one to use the first plastic in clinical practice? It was Sir John Charnley in 1962. Correct? Now, how is this plastic really manufactured? So there are different ways of manufacturing this plastic. First is that you have got fine powder. Now, this powder can be condensed to make this plastic. There are 2 or 3 different ways you can do it. The most common way is called as ram bar extrusion, which means all you do is you take a mold, a big mold, and you put all this plastic, and under pressure, under heat, you make it into a bar. Now this bar you cut into pieces, you do machining and give it a particular shape. Now this is the most commonly employed method, and this is one of the worst methods to make the plastic. We still make plastics with ram bar extrusion. Which is the best way to make a plastic? It is called as direct compression molding, DCM. What it does, you've got an exact mold with the shape of the plastic. You're pouring the powder, you're heating it and pressurizing it and forming the exact shape, exact size with that mold. This is direct compression molding. Why is it better? Because the surface finish, the oxidation at the surface, which you can prevent, all of these is better with direct compression molding. So someone asks you in the exam, what way ideally should a plastic be manufactured? The answer is direct compression molding, right? Now this also undergoes some procedures, which is known as gamma irradiation. Now, why do we irradiate the plastic? It is for 2 reasons. Number 1 reason, that there are a lot of free radicals or molecules over here in the plastic. They are not, there is an amorphous component, there is a crystalline component. You can change the amorphous component to a crystalline component with the help of gamma irradiation. So what it does is that all the covalent bonds are formed after you gamma irradiate, and that gives an increased wear resistance to the plastic. The more the gamma irradiation, the better the wear resistance. But there is one problem in this. The more gamma irradiation you do, the more is the formation of free radicals. There will be covalent bond formation, but there will always be some free molecules which will be floating around. Now, these free molecules can form more if you gamma irradiate the plastic in air. So most of the gamma irradiation that is done in present times is done under inert gas or no air. So either vacuum gamma irradiate or use a inert gas like argon to gamma irradiate the plastic. We also gamma irradiate the plastic to sterilize the plastic. So suppose we have packed the plastic into a box. Now we need to sterilize it before we use it in a patient. So again, the entire box assembly goes for gamma irradiation. Now remember, the first gamma irradiation that the plastic received was to change the composition or the chemical bonding of the plastic. So the dose was much higher. Whereas for sterilization, the gamma irradiation dose that we use is much lower. In previous methods, the calcium stearate molecule was added during the Rambar extrusion process to prevent the yellowishness of the plastic. Now, you might see some of the plastics in your clinical practice, especially with the hip joints, which look yellow in color. Do you think that calcium stearate has not been added and that's why it looks yellow? The answer is that it has been added with an antioxidant like vitamin E, which gives that yellowish discoloration to the plastic. Okay, so I think everyone is clear with about the plastic, that what method is used for the plastic formation. Why do we need to gamma irradiate the plastic? Now, is there any way that we could take away all the free radicals? We know that gamma irradiation makes the wear property better for plastic, but in return, we are doing a lot of free radical formation. How do we take away these free radicals? The foolproof method of taking away the free radicals is by melting the plastic. Just boil it and all the free radicals will go away. But can we do that? The answer is no, because we'll lose all the structural properties of the plastic. So what can we do if we cannot melt the plastic? We can do a procedure called as annealing. Annealing means heating the plastic, not to the extent that it melts, but sub temperature annealing of the plastic. It will take away maximum number of free radicals away by this heating of the plastic, but not all. So it is okay. Even if we can take away 90% of the free radicals with the process of annealing, that's fine with us. So we do a sequential repeated process of gamma irradiation, annealing, gamma irradiation, annealing, gamma irradiation, annealing to obtain an optimum amount of covalent bond formation. Right? So I think that's quite enough about the plastic. Let's move on and talk about some other materials. So let's talk a little bit about the steel, titanium, or the cobalt chrome that we use. The most important things that we can be asked about is what makes these things so special. So have you heard about the 316L steel? Everyone uses 316L steel for their implants or arthroplasty material. Now, what is so special about 316L? What does 316L stand for? The 3 stands for the molybdenum content, 3% of the stainless steel that we are using. 16 stands for the nickel content, which is 16%. And L stands for the low carbon content of the stainless steel. So how much is the carbon content? They might ask you when you say low, how low? So it is 0.03% in 316L steel. Right? What is the special thing about steel? It is very stiff, it is hard, it is durable, it is quite ductile. You can make it lengths and lengths and lengths, and it is quite biocompatible. The other material is the titanium. What makes titanium so special? The titanium comes in titanium 64, where 6 stands for the 6% of the aluminum which it contains, and 4 stands for the 4% of vanadium that it contains. Now, what is good about titanium? Titanium forms an oxidative layer. Whenever it is exposed to the air, it forms an oxide layer on the top of the surface. This process is called as passivation, and it protects the material from external damage. So that's one good thing about titanium. What is bad about titanium? The buzzword is notch sensitivity. The titanium material has got low notch sensitivity, which means that if I scratch the titanium, it is not very resistant to scratching. Even smallest amount of scratching of the titanium will make it lose all its wear characteristics. So initially, the titanium hips, which were the stem was made up of titanium, the head was made of titanium. It has a very high failure rate. Why? Because even smallest amount of scratch, it had such a low notch sensitivity that it would wear out. That's why we do not make titanium heads anymore. When you do a total knee replacement, you have heard of titanium tibial trace, but you would not have heard of titanium femoral component. Why? Because the articular component, surface is between the femur and the plastic, the main articular surface. Whereas the tibial base plate is at the non-articular component. So there we can use titanium because of its all other properties, but it's got very poor wear characteristics. Something about cobalt chrome. So what is one good thing about cobalt chrome? The best thing about cobalt chrome? It is a very high young modulus. So this is very, very tough, very durable, and it is relatively hard, right? Let's move on to our favorite, which is the most talked about thing, which is the ceramic. Now, what is ceramic? Is it metal? Is it non-metal? Well, it is both. We combine metal and we combine non-metal. All other materials are made under low temperature, low pressure. Ceramic is the material which is made under high temperature and high pressure, right? There are minimum voids and it is almost a perfect material. Why? Because the coefficient of friction of this material is very, very low. This material is very, very hard. It has got very high scratch coefficient, right? Which means that it is very difficult to scratch a ceramic. I'm not talking about the stripe wear or the scratching which we see in clinical practice, but we are talking about the material itself, right? It is very, very wettable material, which means that the water molecule can just spread out on it. So this is what is about ceramic. Coming to the next, which is what is wear and what is corrosion. Okay, so wear is a mechanical process, corrosion is a chemical process. In wear, we have three different types of wear: abrasive wear, adhesive wear, and fatigue wear. What is abrasive wear? Abrasive wear is nothing but friction. Two surfaces rubbing on each other, obviously they have friction and that will cause some wear of the surfaces. This is abrasive wear. What is adhesive wear, which we see most commonly in our practice with the hip replacements, with knee replacements, mainly hip replacements, is the one molecule has affinity to the other. So this molecule over here will have some affinity and will form a covalent bond with the other material. So when this material moves, some part of material which was sticking to this will stay with this and detach from this, which means that there was an adhesion, there was a bond formation, and that's why the material is separated. This is called as adhesive wear. What is fatigue wear? Small amount of damages. Now, where do we see fatigue wear? TKR, knee replacement, plastic. Small microscopic wears within the entire material, especially just beneath the surface, which accumulate over a period of time. And finally, at some point in time, after the endurance limit, when it goes away, that is the fatigue wear, also called as delamination. Now, types of wear and modes of wear are two different things, and this will be particularly asked in your exam with regards to hip replacement. That what are the types of wear, what are the modes of wear, and it is very, very common to interchange these two things in the exam. What are the types of wear that we talked about? Adhesive wear, abrasive wear, and fatigue wear. But what are the modes of wear? Modes of wear are four types: an articulating surface with another articulating surface, which means the head of the femur along with the acetabulum. So cup, that is mode one wear. Second type of wear is an articulating surface with a non-articulating surface. Suppose the plastic has worn out and now the head is rubbing against the metal back of the cup. That is the second mode of wear. What is the third mode of wear? It is the third body, which means that there is some impurity or there is some cement particle which has gone into your joint, and that acts like a third body. Suppose there is a small stone which goes in your shoe, so that acts as a third body wear, right? Similarly, we have the last, which is the fourth mode of wear, which is a non-articulating surface with another non-articulating surface. Where do we see this? Trunnianosis. So you might have undergone, must have written short note on trunnianosis in your postgraduate exams. So this is a practical application of trunnianosis. What is trunnianosis? Is the fourth mode of wear where a non-articulating surface rubs against a non-articulating surface, right? So this was wear. Lastly, about corrosion. What was corrosion? Corrosion was a chemical wear where there is a current flowing in the form of galvanic corrosion, or there is a pH change with the help of crevice corrosion. So these are different types of corrosion where there's a chemical change and causes wear of the material, right? Let's move on. So why is a ceramic surface better than metal surface? We all have answered in the exam that I will do a ceramic on ceramic hip replacement as compared to metal on poly or whatever. It is because of this. Whenever a metal scratches, there is this depression, which is called as a divot, and this projection, which is called as an aspirate, right? Whereas whenever a ceramic scratches, there is only a divot, there is no formation of an aspirate. So the friction that this metal will cause will be much more as compared to this ceramic. And that's why this is called as the scratch profile of the ceramic, which is far superior as compared to the metal. Does the head size matter? Yes, we always say that we use as large head size as possible because we want to avoid dislocation. Whereas Chanley said that use as low head size as possible, 22.225 millimeter only. Why? Because he does not want a lot of volumetric wear. So there's a very nice paper by Livermore in JBJS American in 1990, where he says, as you increase the head size of the femur, the linear wear is going to decrease, but the volumetric wear is going to increase. So there is one perfect number according to Livermore where we have balanced out the linear wear and the volumetric wear, which is the head size 28. Does that mean that we should use a 28 head size for all our hip replacements? The answer is no. The study was done in 1990. The plastic that was available at that point in time was a UH, ultra high molecular weight plastic, and there were no XLP, highly cross-linked plastic available at that point in time. However, for exam point of view, for FRCS point of view, you can always quote that Livermore suggested in 1990 that to balance the volumetric wear and the linear wear, we can use a 28 head size plastic, which is perfect, which is not a problem at all, right? So let's move on to the next. So what are different types of lubrication in the normal joints? So we're just going to touch upon this topic because it's a very vast topic, but just to give you an idea that there are three types of lubrication within the joint. So if two surfaces were to collide with each other, so if these are the two surfaces and if they have to come with each other, if there is a big column of fluid in between, it will never, that fluid is not going to allow these two surfaces to ever touch with each other. And that is called as fluid film lubrication, which means that the layers of fluid keep the surfaces apart. The second type is the boundary lubrication, which means that these two surfaces are very close to each other, very much together, and there is a single layer between the two. And what is this layer made up of? Surfactant, the things, something which we have in our lung. So similar to that, which has very low coefficient of friction, like lubricin. It's a glycoprotein released by the articular surface and forms a molecular monolayer. And because of the decreased surface tension, the two surfaces do not form a lot of wear particles because of this surfactant. So this is called as boundary lubrication. I told you that there were three types of lubrication, which is the third one. The third one, which is the most common, which is present in all our substances, which is a mixed lubrication, which means that at some occasions we'll have a fluid film lubrication, at some occasions we'll have a boundary lubrication, in some occasions we'll have a mixed lubrication, right? So this can be the question in the exam which can be asked, that during your gait cycle, during different phases like early stance, mid stance, late stance, and swing phase, which are the different forms of lubrications that you see? The fluid film lubrication, the boundary lubrication, and these also have got further differentiation into elastohydrodynamic, squeeze film, boosted, which you all need to read up with regards to lubrication. Okay, so another question which can be asked in the exam with regards to lubrication in our total hip arthroplasties is, what is Strayback curve? Strayback curve is nothing but a curve which determines what form of lubrication is happening in a particular joint. It is a graphical representation of the lubrication characteristics of a joint. Now, if the fluid film thickness increases, we are going more towards the boundary lubrication. If it decreases, we are going more towards the fluid film thickness increases, we are going more towards the hydrodynamic, that fluid film lubrication. And once it decreases, we are going more towards the boundary lubrication. So here we come across the lambda ratio, which means how thick is the fluid film, right? So if the fluid film is very thick, if the lambda ratio is more than 3, we call it a fluid film lubrication. If it is less than 1, we call it a boundary lubrication. But if the lambda ratio is between 1 and 3, we call it as a mixed lubrication. Right? Now, you will be given some hypothetical scenarios in your exam, which will say, you have been asked to design a hip or knee replacement. How will you do that? What features do you want in that? And there will be always at least one hypothetical question in your exam. Right? So you need to think out of the box. You have to think about everything, not just about the biomaterial. Of course, in the biomaterial, we'll talk about that the material should be inert. The bearing surfaces should have high resistance to wear. It should be easy to fabricate. The cost of the material should not be very high. So these things are there. But you also need to talk about whether the material is going to be modular or whether it is going to be monoblock, whether it is for primary surgery or for revision surgery. How are you going to fix that material, whether it is going to be cemented or uncemented? So all these things will be important. Also talk about that I cannot just make an implant. I will need to make the instrumentation also for the same. The second question which can be asked is that there is a new hip replacement which has come in the market. Now, before it is commercially available, what all things it should undergo? Can you make something in the lab and then directly start using it in the humans? The answer is no. So it has to undergo a robust process of authorization. Now, what is this robust process is what we want. So number one is that we need to get the design approval. We need to test it in the mechanical lab where we are doing 10 million cycles on that implant quickly and checking how much is the wear, right? We need an ethical approval. We need a licensing authority to regulate. And we need a small clinical trial. You cannot start using it in millions of patients from day one. So a very high volume center, which does a lot of joint replacements, will take up this implant. They will do a small clinical trial in a few group of patients, taking their approval. And in these patients, you are going to do an RSA analysis. This is the answer which is expected in the exam. What is RSA? Radioisotope stereotactic analysis. So that is the analysis that you will do in this small number of patients. Once you're happy with your RS analysis, you will do a large clinical trial. And then you will compare it with another implant of the same category, which is already successful. And that is called as the ODAP rating, ODEP rating of an implant. So like for suppose if Depuy synthase has got PFC implant, it has got an ODAP rating of 10A, where 10 stands for that this implant has been proven to be doing well for more than 10 years. So any implant in the market which has been there only for the last 5 years cannot have a 10A rating. It will have for that many years ka rating. If it is 3 years, then you get a 3A rating, right? So that is again very important. Now we'll quickly run through just few more concepts. So what is the key difference between a Charnley stem and an Exeter stem? This is a most commonly asked question in tribology and arthroplasty in the FRCS exam, that you will be given a picture of a Charnley and an Exeter and you'll be asked, tell me what is the difference between the two. the most important difference that you have to say is that the Exeter is a polished tapered stem working on the principle of controlled subsidence, right? Whereas the Charnley stem works on the principle of a composite beam. Okay, these are buzzwords. You need to remember this. What it means is that the Exeter stem depends upon creep. It is bound to subside. Whereas a Charnley stem, it is a composite beam. It is supposed to be fixed in one particular place. If it subsides, then it fails. If a Charnley stem subsides, it fails. Right? I'm talking about the original Charnley stem, not the C stem. The second difference is that stress shielding is very likely in the Charnley stem because of proximal stress shielding. Okay. So one more question that can be asked is about the past failures of the implant. So they can ask you that why did the Charnley elite stem fail? So there was a study which was done, which was a radioisotopic study, and which suggested, this was published in 2003 in JBGS, which suggested that the Charnley elite failed because of high posterior head migration. So in the plastic, the head would migrate posteriorly, and that is why the Charnley elite stem failed. There are reasons that why we did go into that, but let's not get into it because it will save us some time. You can be asked about the NJR. Why was the NJR made in the first place? What is the requirement of a joint registry? As you all are aware, we have now the Indian joint registry. Why do we need a joint registry? Because we need to know that in a longer run, are we going anywhere wrong? Did we realize in the past that we went somewhere wrong? Of course, we had the metal on metal hip, we had the 3M capital hip, and those were the disasters in the past which made us to form a national joint registry. What does a national joint registry tell us? It tells us various implants, various techniques, a CR versus PS, cemented versus uncemented over a period of years, and different nationalities have got their own joint registries. So they might ask you about a particular year, that what, so they usually they ask you about the latest joint registry report, that tell me in the latest joint registry how the unis performing, how the totals performing in compared to unis. So all those things you need to know about the latest joint registry data. What is the problem with the 3M capital hip? So 3M capital hip was launched by the 3M company in 1991. Now they launched it as a very low cost hip replacement material. So the new version was very cheap. It was almost like the Charnley stem, except for there were no flanges in the Charnley as compared to the Charnley stem. The material was made up of titanium. And we remember from my previous description that titanium has got a very poor wear characteristic. It has got low notch sensitivity, and that's why 3M capital hip was a big disaster. In 5 years, almost 20% of the hips failed, which is 4 times more failure as compared to 10-year data of a normal Charnley stem. So that's why this called for formation of the national registry. Okay, we all know about the Gruen and Charnley zones. I'm not going to go into much of detail of this. We know the zones 1 to 7. One thing which will be asked to you in the, everyone talks about the Gruen zones, but no one talks about the Gruen's modes of femoral loosening. The femoral stem can become loose, and Gruen described 4 different modes of how a stem will become loose. Whether the stem will become loose at the metal and cement interface, or whether it will become loose as cement and bone interface, whether it will medial pivot or it will calcar pivot, whether it will be held at the cantilever, which is the distal fragment, and the upper part can move and the stem can break. So there were 4 different modes of failure of the femoral component, and these were described by Gruen, and this will give you really good marks in your FRCS exam, and I want you all to read this up. Right. So what is osteolysis? Why does osteolysis happen in the first place? It happens because of the wear particles. Wear of what? The plastic. The plastic particles are engulfed by the macrophages, and these macrophages will release TNF alpha and interleukin 1, and this will elicit an inflammatory response, and our own body's inflammatory cells will eat up that bone. How? With the help of osteoclastic resorption. So are these plastic particles eating up the bone? The answer is no. They elicit an inflammatory response, and osteoclast will cause osteolysis. What was the problem with metal on metal? Was the metal particles causing a lot of osteolysis? The answer is no. The metal particles that were generated were very small in size. They were submicron particles, right? But a lot of particles were getting generated. It did not do anything to the articular surface. It did not cause any osteolysis. But what it caused was pseudotumors. There are different terminologies that you will hear: pseudotumors, alval, which is aseptic, lymphocytic, vasculitic infiltration. But there is only one term which is used now, which is called as ARMD, which is ARMD, which is adverse reaction to metal debris. So these metal debris cause adverse reaction in the form of soft tissue problems. The soft tissues literally melt away, and that was the main problem with metal on metal. The second problem that we found was the metal on metal particles were found to be teratogenic in animal study. Has metal on metal caused a cancer? We always worry that metal and metal will cause cancer in humans, but it has been proven only in animals. And that's why it was avoided in young females at that point in time. I don't think that there are many centers left which do any metal on metal resurfacing anymore, right? So you will be asked about metal on metal because it was a big failure in the past, and we need to learn from our failures. It brought the joint registry in, and a lot of medical legal aspects going around metal and metal. We need to know about the cobalt and chromium levels in the blood, which are significant, and how do you identify that this metal on metal needs a revision surgery, right? You will be shown a THR prosthesis and you'll be asked to talk about the different parts of it, and you'll be asked that what is the difference between kinetics and kinematics? Are they the same? So kinematics would mean that when you study the motion between two objects, whether it is a bearing surface or anything, kinematics will study motion between two objects. Kinetic will study the force which caused the motion. So if I push something and that caused motion, when I'm studying the force, that is kinetics, but I'm studying the motion of the object itself, it is called as kinematic, right? We are coming to the last few slides, which is mechanics of contact point of the femoral contact in the tibial tray. Now this is very, very important, and why it is, we'll talk about it. So there are two types of implant which we have, CR and PS, right? Cruciate retaining and posterior substituting. What it does is hypothetically, the CR implant allows the femoral rollback, which means that the femoral component can slide over the plastic. Whereas in PS, the femoral component cannot slide over the plastic. Now, those who like CR, they will say that biologically, our own natural knee is bound to roll as well as slide. So a CR component is definitely more biological, more natural to the natural knee as compared to natural knee as compared to a PS component. The PS people will say that the plastic of the CR is not as curved as compared to the PS. Why? Because if it is completely curved and conforming to the femur, then it will not allow sliding. Whereas a PS is more conforming. So they say that the plastic is in more contact with the femoral component, which means that the stress is distributed evenly. There are lesser chances of contact stress points on the plastic, so increases the life of the plastic. That is what the PS will say. So this brings us to the concept of what is congruity, what is conformity, and what is constraint. And this is the most difficult topic, and that's why I've kept it for last. Congruency means that how two surfaces match each other in form of shape. So if this is one surface, this is another surface, how they match each other in the form of shape is congruency. What is conformity? Congruency was a static concept, means statically in one position. Conformity is in motion. In a particular motion, how two surfaces interact with each other in different range of motion of the joint. That is conformity, and that is more important than the congruency, because it is a joint, it is going to move. So we need to know the different positions, how it interacts with each other. Lastly, what is constraint? Constraint defines the level of freedom of a joint. If I'm using a hinge implant, it has got more constraint. It has got lesser degree of freedom. So there are different levels of constraint. For example, unicompartmental knee is the least constraint, followed by rotating platform, followed by cruciate retaining, followed by cruciate substituting, followed by VVC type of implant, followed by rotating hinge, and finally a fixed hinge. So we have increased the levels of constraint. So I hope everyone is clear about congruency, conformity, and constraint, right? So which primary knee replacement you would use? You can say anything. You can see a cruciate retaining implant, you can see a posterior substituting implant, but you need to justify it. You need to say whether I want a biological sliding motion or whether I want a more conformity so that I have less wear. Now this TKR has failed with the help of with the process of delamination. What does it exactly mean? What type of wear it is? So the answer here would be a fatigue wear, which would mean that adhesive wear, abrasive wear, fatigue wear. These are three different types of wear. Whereas most commonly in hip replacement, we have adhesive wear, which is the most common cause of failure. Right? I think that finishes my presentation. Dr. Gopal, are you still there?
Yeah, you can hear me?
Yeah.
Okay, great presentation, Akash. I think you've covered everything for the FRCS. I mean, at least part of it. I know it's huge. You can't cover it in one single lecture. So it has been a tremendous lecture and great learning for everyone. And I'm sure we can have more lectures. I'm sure you're going to be the next big FRCS trainer from the country.
Thank you. Thank you. I think the presentation would have generated more questions than answers because people will start to think. The whole purpose of this presentation was to make people think that why we are doing something, what we are doing.
Yeah, sure. Okay, thank you very much, Akash, and let's get the next webinar very soon.
Sure. Thank you.
Thank you.